Okay, uh, so in the last couple of classes, we looked at a different approach for designing codes, good codes. Initially, we started with an algebraic approach. We studied the class of Reed-Solomon and Reed-Muller codes. They have good minimum distance properties, but unfortunately, they require high field sizes. And well, the decoding can be made fairly efficient, but for example, if you want to transmit over a binary symmetric channel or a binary erasure channel, they're not capacity achieving. They're far from being capacity achieving. The question is, can we design efficiently encodable and decodable capacity achieving codes? Right? And how do we design such codes? How do we design efficient algorithms for encoding and decoding? So we saw one very efficiently encodable and decodable class of codes that were convolutional codes. Both encoding and decoding can be done in linear time, but it turns out that they don't really achieve capacity. They're far from being capacity. Right? So now, again, the question is, well, how do we decode good codes? We know that if we select a code at random, the binary code completely at random, then this code is in fact capacity achieving, provided you do maximum likelihood decoding. So now we have these two situations. One, convolutional codes, which are very efficiently encodable and decodable, but they're bad. But then on the other hand, you pick any code, any block code at random, it's capacity achieving, but unfortunately you cannot encode or decode it efficiently. So where are we? How do we design a good code? So that was the state of things till in the 70s. Robert Gallagher invented this new class of codes called low density parity check codes. They're a subclass of linear codes in which the parity check matrix has a very special structure. Now, for this class of codes, we can design some efficient algorithms, but they were not known to be very good. Now, if you take the class of LDPC codes and do maximum likelihood decoding, then it turns out that they can achieve capacity. So you pick a random so-called LDPC code and do maximum likelihood decoding, use it for, say, the BEC or the BSC, that will get you close to capacity. And there's an efficient algorithm, but unfortunately, if you use the efficient algorithm, which is suboptimal, it's not ML decoding, it doesn't get you close to capacity. That was the state of things till about 2000 or so, wherein we saw that a slightly different class of LDPC codes with a, again, efficient algorithm can in fact get you close to capacity. They perform very well. And that is precisely the class of codes and algorithms that we'll see from today onwards. And this in fact has its roots in the approach is essentially similar to what we did for the generalized distributive law. Right? So if you recall, we saw that the problem of ML decoding of any linear code can be expressed in the following form. Right? It's a maximization process. And now, suppose that I only want the following. Right? Suppose I want argmax over all xi. Okay, I want to find the maximum likelihood estimate of the ith bit. Okay, p of y1 to yn given xi. I don't really care about what the other bits are. Suppose I just simplify the problem to find the ML estimate of the ith bit only, ith code word bit. Then I can basically write this in the following manner. So this is equal to argmax over xi of the max of all other xj's of p of y given xn, yn given xn. So this is argmax over xi of max over x1 up xi minus 1 xi plus 1 up to xn of py on given xn. Okay. And what is py n given xn? I can write it in the following form. Okay. We've seen this before. So it is equal to the product I going from 1 through n of pyi given xi times these local functions, each corresponding to one of the parity checks. Right? So this is equal to 1 if the jth parity check is satisfied, and equal to 0 if the jth parity check is not satisfied. Right? And for this, we also saw a particular factor graph. We saw what the factor graph looked like, or what the junction tree looked like if the factor graph has no cycles. But anyway, let's pause at this particular thing for a moment. So suppose I have an efficient way of doing this. Okay? Now this, remember, is only going to give you the bitwise maximum likelihood estimate, the ML estimate of the ith code word bit. Correct. So this is one way of computing the ML estimate. The other way, so this is in fact the blockwise ML estimate, but you can also find the code word bit ML estimate in the following way. Argmax I n n. So now suppose I just want xi. I want to maximize this particular quantity. Okay. I can write this as argmax over all possible psi summation x1 up I minus 1 I minus 1 n of py1 up to n 1 up to xn. Correct? And this is equal to, again, I can replace py1 through yn, x1 through xn as py1 through yn given x1 xn times px1 through x, which is some constant times this. So there's some renormalization required for the probability of x1 through xn, but all code words occur equally likely. Okay? They all are uniformly drawn at random, assuming that the message bits are uniformly distributed. The code word bits are also uniformly distributed, as long as they're valid code words. So all code words are equally likely, and therefore maximizing this is the same as maximizing argmax over xi x1 up I minus 1 I plus n of p of 1 n given x1 up to n times indicator that xn is a valid code. Correct? Which is the same as this quantity. argmax over all possible I summation x1 up to xi minus 1 xi plus 1 up to xn. Okay. Now, what is this problem? This is just a marginalization of a product function. And that too, this is over the sum product semi. So, and we know how to do this efficiently as long as the junction tree can be constructed efficiently. Does not have too many vertices, too many edges. Right? Remember that the complexity of the generalized distributive law essentially depended on the sum of the degrees of all the vertices. So as long as the number of vertices is small enough, grows linearly with n, and the number of edges is roughly a constant or not too large, the overall complexity is also reasonably small. Okay. So now if we can do this, then we can find the bitwise estimate of the ith code word bit. And if we do this for all code word bits, then it gives us some estimate of the entire code word itself. Right? So basically, maybe you can run this n different times, or maybe you try to parallelize the algorithm and find x1 hat. So let me call this xi hat. So I find x1 hat, x2 hat up to xn hat, and this gives me one decoding rule. The question is how does this decoding rule work? Is it good or not? So let's again quickly recall the factor graph or the junction tree corresponding to this particular to this particular problem. Right? Remember that these were the corresponding. So this was one factor graph. Remember, there were 2n variable nodes and n minus k plus n check node. Right? So the main processing really is basically done in this part of the factor of the junction tree. Right? But remember, this works. So this is in general the factor graph. If the factor graph does not have any cycles, then this turns out to be the same as the junction tree. But if this factor graph, basically this part of the factor graph, has cycles, then this is not equal to the junction tree. So the factor graph is the same as the junction tree if the factor graph has no cycle. And in this case, we know how to perform these operations very efficiently. Correct? But as I mentioned earlier, this doesn't work in this is not very helpful, because if we look at a factor graph which doesn't have any cycles, it doesn't have good error performance over PSC or BEC or any other channel. In fact, it turns out that it has very bad minimum distance properties, and as a consequence, it's not going to perform well over any possible channel. So then what do we do? Do we just give up hope? Suppose that I try to use something like the GDL, even if the factor graph has cycles. I'll try to adapt it to any general factor graph. So let's quickly recall what the rules were. Basically, the GDL worked by passing messages from one vertex to another vertex. Along each edge, you pass a particular message. Right? So there were two components. One was a rule. So how do you initialize the messages, what each message corresponds to, and how do you update the messages? What is the updating rule, and what is the updating schedule? So in what order do you update the message? So let's first look at the update rules. Right? So in general, the message from the ith vertex to the jth vertex, correct? So this is a function of sj minus, sj intersection si, right? So you first marginalize all the variables which are not contained in sj of alpha of x will be xsi, okay? Okay, alpha of xi times the product all the neighbors, all the other neighbors other than I, product overall L, which are in the neighborhood of I but not containing j, of the messages so this was the scenario. You have ith node, you have a bunch of incoming messages and one outgoing message. So this is to node j, okay? And the message along this edge was denoted mu I to j. Okay, this is mu to j, whatever the neighbors of I are. So these are the L's, these other vertices are the L's, and this is the j. So the message being passed from I to j is obtained by taking the product of all possible incoming messages, multiply it with the local function corresponding to this node, and then marginalize with respect to everything other than what j requires. That was the general rule. All right. So now let's go back to this factor graph. Okay. And in this particular factor graph, let us think about the schedule. In what order? Suppose I wanted to get an estimate of x1. I want x1 hat. What would I do? So obviously these would be the sort of vertices, right? These would be the leaves of the junction tree because all of them have degree exactly. So you have messages going from here to here and then from here to here. So you have something from y2 to p y2 given x2 to x2. That would have to go to this particular check node. From this check node, it would go to xy and so on. Right? So you basically take this particular junction tree. You take maybe x1 as the root of this junction tree and then propagate all the messages from the leaves to this particular root. In other words, if you think about it, this can be done in the following way. You start with, so these vertices are kind of neatly partitioned into two, right? So these are kind of variable nodes and these essentially correspond to checks. So suppose that we do the following. You start with the variable nodes. The variable nodes send messages to the check nodes, right? And the check nodes, remember that every check node is only connected to variable nodes and variable nodes are only connected to check nodes, right? It's a bipartite graph. So I can do it in stages, right? Message, so variable nodes to check nodes and check nodes to variable. I keep repeating this until this algorithm converges. So I anyway need, if this is a junction tree, then anyway I'll need to do only a finite number of steps, whatever that number may be. So now I'm going to propose an algorithm which works essentially similar to the GDL, right? And the schedule is always going to be the following. The messages are going to be sent from variable node to all check nodes, from all check nodes to all variable. And you keep repeating this until it converges, right? So this is an algorithm which I'm going to call belief propagation. Okay, so this first requires some initialization. Okay, so the belief propagation algorithm is basically going to run on this particular graph. So let me redraw it in the following manner. Going to be y1, y2 up to yn, x1 to xn, p1 to cn minus k. So the schedule is going to be the following. You initialize each of these nodes, py1 given x1, py2 given x2 up to pyn given x. So y1 through yn is what you have received, right? That is fixed. And pyi given xi is also given to you, right? So these are going to be vectors of, for example, if it's a binary linear code, then these are all going to be vectors of length 2. Pyi given xi. So py1 given 0, py1 given 1, py2 given 0, py2 given 1, and so on. So these messages are going to be passed to each of these xi's. Remember that this is a function of x1. This is also a function of x1. So there's no real marginalization to be done. This is going to be sent exactly. Pyi given xi is going to be sent to all of these x. So from this point onwards, we are going to do the following iteration. Okay? So there are going to be some messages being passed from each variable node, each of the nodes over here, to each of these nodes over here. So these nodes marked in blue are called variable nodes, and each of the squares marked in yellow are going to be called check nodes. So in parallel, I'm going to compute whatever these many messages, one for each edge, from each variable node to each check node, each of its neighboring check nodes. And once I compute all of these messages, I'm going to compute another set of messages from each check node to each of its neighboring variable nodes. So that is going to correspond to one iteration. And I keep repeating these iterations until convergence or until some kind of stopping rule is reached. Okay. So the initialization is going to be done as follows. So you're given the received vector. We first compute Pyi given x. Okay, so for now, we only focus on binary codes. So each xi can be 0 or 1. So it's going to be a vector of length 2. Okay. And next, until some sort of convergence is reached, you do the following. First, you have from variable nodes, maybe I should do it in 3 first one. Check node. So from, let us say, the ith variable node, from the ith check node to the jth variable node, the message is going to be obtained in the following manner. Now each of these messages is going to be a function of x, okay? And this is equal to summation over all. So remember, what is the jth check node? Sorry, the ith check node a function of? It's basically a function of all the x's which are neighbors of this particular check. So it's the neighborhood of the I, but not j, right? So you want to marginalize with respect to everything that is not equal to j. I all the incoming messages. Correct? But each check node, you take one particular check and look at all of its neighbors. This is the jth check node. 1, 2, is not m. Maybe. So maybe the jth check node has m neighbors, and I want to compute the message along this particular edge, that is from Cj to Vim, right? How do I compute this? So I take the product of all possible all the other incoming messages, right? I multiply it with the local function, and then marginalized with respect to everything else except xim. Right? That's exactly what I have written over here. So I take the product with respect to all other, take the product of all other messages. I multiply with the local function. What is the local function equal to? Yeah, correct. So what does it look like? But pyi given xi does not correspond to the check nodes, right? That's not the local function. What is the local function corresponding to the check nodes? It's this one, the jth parity check. So it's the indicator that your summation over all j is equal to 0. So this is indicator from summation L in the neighborhood of I xl. This is equal to 0. And remember, this is performed modulo 2. This summation is really an XOR. Okay, so this is what I do at each check node to compute the message from a check node to a variable node. Now, what do I do from the variable node to check node? Right? So each variable node over here, this particular thing. So each variable node is connected to a bunch of check nodes, but it's also connected to one of these. Right? What can you say about the variables corresponding to each of these edges? What are the local domains going to be? That is there, I agree. But remember, so this check node, for example, let us take this concrete example. So there's a local function corresponding to this check node. What are the variables? What is the local domain corresponding to this particular check node? It is x1, x3, and x4. What about this particular check node? x2 and x5. Right? What about these variable nodes? Each of these variable nodes are also associated with some local domain. What are the variables associated with this local domain? No, those are the local functions, right? The variables are x1 through xn and y1 through yn. Those are the only variables involved, right? So what variables correspond to these local functions? No, it's not a function of yi, right? These. It's just xi. So each of these local domains contains exactly one variable, xi. And all incoming messages are functions of only xi. Outgoing messages are also functions of just xi. Right? So This is the check node. You take the ith variable node, this pyi given. Okay. But what about these messages? This is some, maybe this is 1 3, maybe this is v. So mu 1 to v is a function of just xv. Similarly, this one, mu 2 to v, is just a function of xv. And the outgoing message is also a function of v, is also a function of xv. So again, let's use the rule for TDL. You take the product of all incoming messages, you multiply it with the local function, and then marginalize, correct? But all of the incoming messages, so it's at the variable node, you take the product mu 1 to v of xv, mu 2 to v of xv. The local function is just actually an identity times p by v given xv, and there's no marginalization to be, right? Because everything is a function of xv. The outgoing message is also a function of. So therefore, at each variable node, all you have to do is multiply the incoming messages. So mu ej I, this is a function x a. This is just the product, so it is p yj given xj times the product of all neighbors to so you keep repeating this until a certain stopping point is reached. So just to denote that this is an iterative algorithm, let me indicate this with respect to time. So in the tth iteration, you do the following. You first update the messages from check nodes to variable nodes. So this depends on what is sent at iteration t minus 1. And this is iteration. Okay. So initially, you initialize all the messages. You p equal to t j given this is some algorithm. So it's basically the generalized distributive law if the factor graph does not have any cycles. Okay? So if it doesn't have any cycles, this will give me the ML estimate. If it has cycles, then I have no idea how this will. Okay. So we have something. Let us see how this algorithm would work in some special case. So it turns out that, for example, if you take the BEC, then this algorithm can be simplified somewhat. Okay? So for the BEC, I'll provide a simplified algorithm. Okay, and the algorithm is the following. So first, you have initialization. Which is done in the following way. So you label all variable nodes with the received value. Okay, so xi of 0, this is equal to yi, exactly what has been received. Okay. And then you perform the following iterations. So from the ith variable node to the jth check node, so which is its neighbor, this is going to be exactly equal to xi of t. So whatever is it has currently, it is just going to spread this information to all its neighbors. And then at the check node, I'm going to do the following. Okay. Vi. So the message is going to be the following. So it is going to be the XOR of all of everything else if all messages are binary. So if all of them are non-erasures, then I'm going to send the XOR of all of those. Otherwise, I'm going to send an erasure. And at the end, I'm going to set xi of t1 be equal to any of maybe let me represent this pictorially. The rules are going to be the following. From each check node, I have a bunch of variable nodes. So each variable node is basically going to send the value of xi that it has currently. Right? So some of these could be erasures, some of them could be non-erasures, 0 or 1. Right? So now I want to compute the message, this particular message along this particular edge. If all of the other edges are symbols which are not erasures, if they're all either 0 or 1, then I take the XOR of everything I have and send it along this edge. If any of them is an erasure, then I send erasure along this edge. Okay. Now what do I do at a particular variable node? At each variable node, I sort of recompute my estimate. If any of the incoming messages is not an erasure, then I take that value over here. If my previous estimate was already not an erasure, if it is 0 or 1, then I leave it as it. If one of these, suppose that my previous estimate was an erasure and one of these is not an erasure, then I take that, I update it with that particular value. If all of them are erasures and my previous estimate is an erasure, then my next estimate is also erasure. Okay? So let's maybe see an example. So let's take some parity check matrix. Suppose I have this particular parity check matrix. Okay, 1 0 1 1 0 0 1 0 0 1 1 0 0 1 0. Okay, so let me draw the factor graph corresponding to this. So there are 5 variable nodes and 3 check nodes. So the first check node involves x1, x3 and x4. Okay, and the second involves x2 and x5. And the third one involves x1 and x4. Right? Okay, so now let us suppose that the received vector is the following. So it is be 0 0 erasure 0 0. Okay. Or maybe let's try to complicate it a little bit. Suppose 0 0 erasure erasure 0. Right? So initially, so this is how we are going to initialize this. And now you compute the message along all of these edges from left to right. Each node is basically going to send exactly what it has. Erasure, erasure, 0, erasure, 0. So now you need to compute the messages from the check nodes to the variable nodes. So let's try to compute this. So suppose I want to find the message along this particular edge, right? From this check node to this variable. So you look at all the other incoming messages. I have 1 erasure, 2 erasures. So both of them are erasures. It's going to be. What about this one? Have one of the incoming messages is a 0. The other one is erasure. So the outgoing message is also going to be erasure. Correct? So even if one of the incoming messages to a check node is an erasure, the outgoing message is going to be erasure. The same holds for this case. Is this okay? Fine. Now let us compute from this check node to this variable. The incoming message is 0. The outgoing message is going to be the XOR of everything, all of these. So this is 0. Nothing else to do. The same holds for this case. The outgoing message is going to be 0. Okay. Now let us take this check node. One of the incoming messages is an erasure. So this outgoing message is also erasure. Agree? What about this one? So there's one other neighbor, which is when the incoming message is a 0. So this is going to be 0. Right? Okay. So now let's see if anything needs to be recomputed. So the previous estimate is 0, nothing to be done. Previous estimate is 0, so nothing to be done. Now take this. This is the first erasure that we have run into. Look at all the possible incoming messages. It has only one incoming message, and that is an erasure. Right? So nothing to update over here. Take this one. There are two incoming messages. One is erasure, the other is 0. So which means that I can update this. I update this to 0. Okay. Now let us recompute all the messages. The outgoing message is exactly what it has currently. So this is 0, 0, erasure, 0. So this we've got some improvement since the first iteration, or the 0th iteration, because we've essentially corrected one of the bits. Okay. Now let us recompute these messages from the check nodes to all of the variable nodes. Okay, what should this message be? Erasure. What about this one? So one of the incoming, so it has two other neighbors, which is this, and both incoming messages are 0. So the outgoing message is 0 XOR 0, which is equal to 0. What about along this particular edge? It's erasure, because one of the incoming messages is an erasure. Okay. Now, what about along this edge? It is 0. Along this edge, it is 0. Along this edge, 0. Along this edge, it is 0. Okay, so now let's see if we can redo some of these estimates. So this is the only thing, and I have one incoming message which is a 0. Right? No. So that's a rule, the rule that I've given. Now I leave it to you as a homework to show that this algorithm is equivalent to the more general algorithm that I presented earlier. Alright, so far we've just seen sort of handwritten examples, right? Very tiny examples, short block length, and so on. But really, how does this perform for larger blocklets? Right? So for this, I've written a code just to simulate transmission over the BEC. I'm not going to give the algorithm or how I implemented the algorithm. It is the same, exactly the same as I have predicted. But I'm going to give you a homework. So one of the assignments is going to be for you to write the code for decoding this particular, decoding any linear code, give a given LDPC code or a given a linear code using this particular algorithm. Okay. So I'm going to define, so I'm going to simulate this for erasure probability. So it's going to be transmission over a binary erasure channel with erasure probability 0.05 and so on, all the way up to 1. I'm going to use a block length of 100. Okay, and n minus k is going to be equal to 50. I'm going to simulate this for, let's say, 1000 blocks. Maybe just to show it here, change that to 300 blocks because it takes some time. And I'm generating the parity check matrix in some particular fashion. Okay, we'll see how to generate a good parity check matrix in a few minutes. And over this, I want to find what is the code word bit error probability, how many code word bits are in error at the end of this decoding algorithm, and the frame error probabilities, how many blocks or how many frames are not decoded. So basically, I take one code word, 100 bits, transmit 100 bits over the BEC, and then I run this decoding algorithm. And once I decode, I try to find out how many erasures can be corrected. If I correct everything, then the frame error rate, there's a 0 contribution to the frame error rate. If even one of those erasures are still left uncorrected, then it means that the whole frame is in error. The frame is not fully corrected. So that gives a contribution of 1. And I count the number of frames, or basically the number of blocks, which cannot be corrected fully. Remember, out of those 100 code word bits, even if one code word bit, even if there's one erasure left over at the end of the algorithm, then it means that the frame error rate, there's a contribution of 1 to the frame error. It's not fully corrected. On the other hand, if the bit error rate is basically the fraction of bits which are correctly decoded. At the end, how many fraction can be corrected? Right? And okay, so you have a BEC. So in this case, instead of generating random vectors or random messages, I'm always transmitting the 0 message. Okay, just for simplicity. I transmit this over a BEC. I run a particular algorithm over here, and I count the number of errors. Right? Nothing. Let's see how this. So for small erasure probabilities, it turns out that both the bit error rate and frame error rate are pretty small. But as you keep increasing the erasure probability, again, now 0.25 onwards, turns out that it's increasing slightly. this is what the bit erasure probability looks like as a function of up to p equal to whatever 0.25 or around 0.3 or so. The number of bit erasures left over is equal to 0. Beyond that, it keeps increasing and goes all the way. But on the other hand, if you look at the frame erasure rate, how many code words have at least one erasure left over in them, it turns out that this is close to 0 for p less than 0.25 or so. But then beyond that, it increases. After that, it is 1, which is similar to what we talked about when I discussed the Shannon's channel capacity, right? So if you take large enough block lengths, then for a certain rate, as long as you operate at a rate below capacity, the probability of error is almost 0. But as soon as you try to operate at a rate even slightly above the capacity, the bit error or the block error probability tends to 1, right? Which is exactly what is happening over here. So basically, below capacity, probability of error, probability of block error is close to 0. Anything above that, probability of block error is close to 1. Of course, I'm using only n equal to 100. But now if I sort of increase n to say 1000 or 5000 or something, you'll see a more sudden transition from 0 to 1. But there's one thing to note over here. So what is the rate I was using? What is the rate of this code? Half. It's a rate half code. So for what p is half equal to the capacity? What is the capacity of a BEC? You remember? What is the capacity of a BSC? So 1 minus H2 of P. That's the capacity of the BSC. The capacity of the BEC, if you recall, is 1 minus P. Right? So in other words, it makes sense to talk about that erasure probability below which you should be sort of be able to transmit almost noise free, and above which you should be able to not be able to transmit anything. So in that case, what should be the threshold erasure probability? So for what erasure probability is the capacity going to be equal to half? Half, right? So if I take any p, which is, so since I'm operating at rate equal to half, for any, according to Shannon's channel capacity theorem, I should be able to transmit over any erasure channel noise free as long as erasure probability is less than half. So really, I should be expecting that the following holds. For large enough block lengths, erasure probability on the x-axis, if I take the erasure probability or the frame error rate, really it should operate in the following. So this is half, then it should be 0. The probability of error should be equal to 0 for p less than half, and it should be close to 1 for p greater than half. So really this threshold should be at p equal to half. But what is actually happening over here? Where is the threshold? Point. Well, okay. So really, maybe something slightly higher, I can say, it's somewhere close to 0.4. It's strictly less than half, certainly, but it's not. It's something greater than 0.3. So this transition is happening because I'm using a p. I'm using n, which is small. So it's somewhere between maybe 0.3 and 0.4, 0.45. That's really where, if I take a larger n, then that is where things are going to transition. Okay? So why is that happening? The reason why this is happening is because this is, in fact, it doesn't achieve the capacity. It can perform essentially very low probability of error transmission at some other rate which is strictly less than half, or some other erasure probability strictly less than half. So this class of codes that I have chosen, I'm choosing the parity check matrix in some particular fashion. Okay? And it turns out that the way I'm choosing it, it does not achieve capacity. It achieves some rate which is strictly below capacity. And we'll see why that is the case. Okay? So now I'll introduce a class of codes, a class of LDPC codes, which are special. Okay, these are called regular low density parity check code. So the algorithm that I just specified, it holds for any linear code. Do you agree? You just have to send messages from variable nodes to check nodes and check nodes to variable nodes. And I can do that for any given linear code. But the GDL, or the generalized distributive law, guarantees that this is equivalent to ML decoding only if the corresponding factor graph is a tree. Now, if the graph is instead something like a tree, it's not a tree, it has some cycles, but it doesn't have any short cycles. Okay? Then it turns out that this algorithm still works well. And in fact, we can give some sort of guarantees. So if the factor graph is what I call tree-like, it has no short cycles, then it turns out that this belief propagation algorithm gives good performance. And also remember that the complexity of the GDL really depended on the degrees. So the overall complexity is proportional to the sum of the degrees of all the nodes. So that is why, in order to keep the complexity low, we'll make sure that all the nodes in the factor graph have very small degree. And this is one specific subset of codes which have very low variable node degree and write node and check node degree. So a DVPC regular LDPC code is basically, they are such that the factor graph is such that each variable node is connected to exactly DV check nodes, and each check node is connected to exactly the variable node. Okay, so this is what I mean by a DV-DC regular LDPC. So what can you say about the parity check matrix? If I look at any particular column, how many ones are going to be there in that? Exactly dv, right? Because each column corresponds to one variable, so each column is going to have exactly dv ones in there. What can you say about each row? Exactly dc. Right? Okay, so now suppose I wanted to randomly choose such a parity check or such a factor graph. How would I do it? Any suggestions? I want to generate a parity check matrix such that every row has exactly DC ones, not less, not more. Every column has exactly DV ones. Yeah. Okay, but how do I? Can you give me something like a pseudo code? Suppose you had to write a code in C or Python or something. How would you do it? Okay. 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 But how do I sort of generate this matrix? I give you to do it however you want. So okay, so let me highlight one of the issues. So one way to pick a random matrix, forget about this, okay, which doesn't get this but something close, would be the following. You take, so you want to basically constructing a random matrix is the same as constructing a random factor graph, right? So what I can do is the following. For each variable node over here, what I basically have to do is choose exactly dv check node. So I can sample numbers from 1 up to dv without replacement, correct? And that is going to give me, that is going to ensure that every variable node is going to be connected to exactly dv check node, right? I can do this for every single variable node. That ensures that the variable node degree is equal to dv for all variable nodes, right? That it ensures that if you look at the parity check matrix, every column has exactly dv ones in it. So that's one way of generating a random matrix. or in other words, a random factor graph. But now what is the problem? DC. So it's possible that some of these check nodes can have degrees much larger than DC. So how do we resolve this particular issue? How do you sample from the class of say DV, DC regular graphs or DV, DC regular parity check matrices? Okay, so maybe taking one step back before that. Suppose that so I give you n variable nodes and say m check nodes. Can DV and DC be chosen arbitrarily, or is there some requirement? Sorry, DC has to be. Why should be n? Correct. DC is the degree of each check node, right? So is there any constraint on DB and DC, or can they be arbitrary? Can I say? Okay, but is that sufficient? Okay, suppose I take n equal to 100, m equal to 50, say dv equal to 3 and dc equal to 7. Is this okay? Okay, my question is, does there exist any graph for which has exactly n left nodes, m right vertices, the degree of every left vertex is equal to 3, and the degree of every right vertex is equal to 7? That many? Why? So this the DC has to be less than or equal to n, right? It has to be less than 100. Is there any other issue? What is the number of edges in this particular graph? Yeah, correct. So there should be 300 edges. But what about the right side? So really, so if I select n equal to 100, m equal to 50, dv equal to 3, then what should dc be equal to? 6. So you can't choose dv and dc arbitrarily. So what is the requirement? What should dc be equal to? N into dv divided by m. So you have to choose this. Okay. Okay, so maybe let's stop here since we're almost out of time. You can try to think about how to generate a random matrix, right, or a random factor graph, which is again both left regular and right regular. Every left vertex has degree exactly equal to dv, and every right vertex has degree exactly equal to. Okay. Any questions?